All right, let's jump right in. Today, we're going to talk about a really profound shift in how we see the universe. It's this idea that the laws of physics, well, they aren't just a bunch of math equations. It turns out they might actually be forced on us by geometry itself. And this one idea, this one change in perspective, is unlocking some absolutely incredible breakthroughs. So we're going to dig into how that works. So here's a question for you. What could possibly connect designing new medicines, building quantum computers, and training AI? I mean, they seem like totally different worlds, right? But the crazy thing is, they're all running into the exact same walls. And even crazier, they're all being supercharged by the very same really surprising and powerful idea. Let's find out what that connection is. Okay, so let's start with this puzzling pattern. To really get to the bottom of this, we've got to look at something a little strange that's popping up all over the place, right at the cutting edge of science. Seriously, something big is going on, and it seems to be happening everywhere at once. You see, for decades, we've been using these pretty straightforward, simplified models to solve problems. And they worked for a while. But now, when we're facing the really big challenges, like trying to understand incredibly complex molecules or quantum systems, or just these massive mountains of data, those old methods, they're just hitting a brick wall. They're not just a little off, they're flat out failing to give us the right answers. But, out of all that frustration, something new is coming along that's just delivering these dramatic breakthroughs. It's having incredible success. And the whole thing, the key to it all is that it hinges on throwing out one of our most fundamental assumptions. I'm talking about an assumption we've been running with for centuries, about how reality itself even works. And you can see this pattern of success everywhere. I mean, look at molecular modeling. We're now designing drugs with what they call chemical accuracy, which is just a fancy way of saying we're getting it right, and that is a huge leap forward. Then you've got quantum computing, where this new approach is literally defining the absolute ultimate limits of how precise we can be. And in AI, it's the secret behind things like natural gradient methods that are training algorithms to be way, way smarter and more efficient. It's wild. One single shift in thinking is just blowing the doors open everywhere. So, okay, what is this big revolutionary idea? Well, to get our heads around it, we have to talk about a concept called state space. Just think of it like a map, but it's not a map of a city or a country, it's a map of every single possible thing a system could do or be. So yeah, a state space is basically this landscape of possibilities. Let's take that protein molecule example. Its state space isn't just the one shape it's in right now. Oh no, it's a giant sprawling map of every single possible shape it could ever fold itself into. Every single twist, every turn. Each one is a different spot on this map. And this is where we get to the big, flawed assumption we've all been making. The old way of thinking, it basically treated these maps of possibility as if they were perfectly flat, like a piece of paper. It just assumed that the shortest, easiest path from point A to point B was always a simple straight line. But that's like trying to use a flat city map to hike across a mountain range. You'd try to walk in a straight line and end up running smack into a mountain. The new way, the curved reality, it actually respects the real terrain of this map. It finds the true path of least resistance, following the ridges and valleys of what's actually possible. Because that's the thing, the terrain of reality, this map of possibilities, it isn't flat at all. It's curved, it's bumpy, and it's anisotropic. Now, that's just a fancy science word, but all it means is that the cost of moving is different depending on which direction you go. Think about that molecule again. Trying to stretch one of its chemical bonds takes a ton of energy, but just rotating that bond, way, way easier. The landscape isn't the same everywhere. Some paths are like climbing a cliff, and others are a gentle stroll. Okay, so if the map of reality is all curved and bumpy, how in the world do we read it? Well, it turns out that physicists have come up with this amazing mathematical tool that's kind of like a universal scanner. It can look at any system, no matter how complex, and create a perfect, detailed blueprint of its state space. It's called the spectral zeta function. And I know that sounds super complicated, but please, don't worry about the name. What really matters is what this thing does. Basically, you can feed it any complex system, and it analyzes the shape of its possibility space, and then it spits out this unique signature, a blueprint that tells you everything you need to know about its geometry. So how does it actually make this blueprint? Well, think of it in a few steps. First, it scans the whole landscape of possibilities for a system. Then, and this is the cool part, it listens to the system's natural vibrations or frequencies. You can think of it like listening to the unique sound a bell makes. From those vibrations, it extracts a unique spectral signature. And finally, it decodes that signature to pull out all of the system's most essential fundamental properties. It's like a cosmic detective. And here's where we get to the real magic trick of this whole thing. This tool doesn't just dump a giant pile of data on you. No, it does something brilliant. It cleanly separates all the geometric information into two totally distinct and super important types, local and global. Okay, so let's break that down. On one side, you have local information. This is all about the immediate details, the here and now. Think of it like the texture of the pavement right under your feet. It's the little bumps and cracks that affect things like motion, diffusion, how a system reacts when you give it a quick poke. Then, on the other side, you have global information. This is the big picture, the bird's eye view. It's not the pavement, it's the entire layout of the city, its fundamental shape, how everything is connected. This is what governs the really big stuff, like a system's overall structure, when it goes through a phase change, and even its entropy. And this separation, this is what explains that mysterious pattern we started with. All those amazing breakthroughs we were talking about in drug design and AI, they're happening because the new models finally respect both kinds of information. They understand the local bumps and the global shape of the causability space. They're paying attention to the texture of the pavement and the layout of the whole city. And that is precisely why they're suddenly so much more powerful and so much more accurate. All right, let's get to the final and, honestly, the most powerful point of all. Because we need to see why this isn't just some clever new trick for building better models. This is way deeper. It's a fundamental rule about how our universe simply has to work. And this quote really just nails it. It says, "A central requirement of physical law is invariance. Geometry is therefore not merely helpful, it is forced by invariance." So what does that mean? Well, invariance is a core principle of physics. It's just the simple idea that the laws of nature have to be the same for everybody, no matter where you are or how you're moving. The laws can't depend on your own personal coordinate system, your personal point of view. And it turns out, the only way to write down laws that actually obey that rule is to write them using the language of geometry. It's not a choice, it's forced on us. This all leads to this one core principle with a very intimidating name, diffeomorphism invariance. Again, forget the name, it stands for a really simple, powerful idea. It just means that the laws of physics have to work no matter how we decide to draw the grid lines on our map of possibilities. The laws have to describe the actual shape of the landscape underneath, not just our arbitrary man-made description of it. And that requirement, right there, is what forces physics to be geometric. So why does all of this matter? What's the big payoff? Well, for one, it gives us a beautiful unifying principle that connects tons of different areas of science. It explains, on a really deep level, why those new geometric models are working so darn well. And it's not just philosophy. It gives us new, concrete predictions we can actually go out and test. But really, the biggest takeaway, the thing to remember, is this massive shift in thinking. Geometry isn't just some passive stage where the play of physics happens. No, the very shape of a system's possibilities is what's writing the script. It's actively dictating the physical laws that run the show. Which, of course, leaves us with one last, really fascinating question to chew on. If a system's geometry dictates its physics, then what dictates the geometry? If the shape of all possibilities is what writes the laws of the universe, then what or who gets to draw the shape?